Uh, Hello, students. So today we will start uh, a new idea, new part of our syllabus is called stochastic processes. Stochastic process. So far we have learned probability theory. Now we will have the modeling of using probability theory or mathematical problems. Okay, and this is part of stochastic process. And in my last lecture, we discussed about central limit theorems. That is one of the major theorem. And you remember that I mean there are other some small inequality which is not so important, so we did not discuss. Okay, but so let us start. What is stochastic process? So let me just give you first intuitive idea, then I will define it mathematically. So I can say that it is uh, a mathematical modeling, a mathematical model of a random experiment, random experiment okay, that evolves in times, evolves in times, okay, in time, and you consider this generates a sequence of numbers, okay, some numerical values, okay, and say you can write down, okay. So evolves in time and generates a sequence of numbers. So let me describe geometrically. Okay, so now you can have two types of such things. Okay, so geometry, let me tell you. So you can have the time may be discrete, like you can discuss describe the time in day to day or hour basis. Okay, so and on the first day, say, and the number of accident in India is something, say, 100, and then in day 2 the number is maybe, say, 200, and day 3 150, okay, and like this. So you can have okay, so number of accidents, and then day 4 maybe it is 250, like that. Okay, so these are kind of so each, like, time 1, time 2, time 3, they are so the values are actually taking some values. So these values are actually, each of those things are uh, um, uh, so these are the outcomes. So these are what probability experiment these values are taking. So what does that mean? So these are all random event, random variables. So these, like, x1, x2, x3, maybe x of t2, these are all random variables, okay, random variables. Or you can have the time may not be discrete, may be continuous, and you can have like the values like something like this. Okay, so at time t, so you'll have xt here. So these xt or t dash, xt dash. So these are all random variables. Okay, so you can understand. So you are writing or giving a numerical value at time t, and that value can be anything which is you know already the values that these can be in the set, but for each time you cannot predict what is the value. That's why these are random variables. Okay. So how to say mathematically? So maybe let me write down the definition mathematically. Definition. So a stochastic process is a sequence of random random variable indexed by time. Okay. So you can have two types of dis- discrete process. So what does that mean? That means here you have sequence like x1, x2, x3, and dot 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 dot. This is kind of a discrete stochastic process, and each of these xi's are random variables. Okay, or you may have continuous process, continuous process, and here you will have kind of xt sequence where t is something say greater than equal to 0 for the time. Okay, so mathematically we define by sequence. Okay, so now let us give you some examples. So for example, the very important example we generally see it in directory basis. So the sequence of say daily uh, price of a stock in share market. Okay, or say sequence of the sequence of number of death for this COVID-19 daily. Okay, this kind of these are example of discrete random variables, and for container random variables also you can write down those things. Okay, and now so what are the questions generally you study in stochastic process? So there are three type of questions generally you study. So questions. Okay, so you can ask that what about the future dependencies? So you can write down future dependencies. So by that I mean that suppose you know you have x1, x2, x3, you know about these. Say you know everything about x1, x2. Can you say anything about the rest other things? Okay, so these are called future dependencies. So this question people ask and people will want to learn so that you can predict the future from whatever you know. Maybe second question, very interesting question, that long-term average. What would be the long-term average? Let me write down this long-term average. So what does that mean? That means in the long term, whether can you predict the value? Okay, right. If you want to buy a share, so you want to know that in the long term what happened. Okay, and then it is the central limit theorem is useful here. So you can think that the application of the central limit theorem, okay. Or you can ask, what about the frequency of uh, frequency of occurrence of uh, some bounded events, so certain bounded events, okay. So what does that mean? That means, so for example, how often the share price drop by say 10% in a day. So these are very rare case. Or share price, stock price up by 20% in a day. These are very rare event. We want to know how often it happened. Okay, what is the probability? So this type of questions generally people study that future dependencies, long-term behavior, and things. Okay. So now, as you know already, this so we have uh, stochastic processes. So you have discrete type and continuous type. Okay, and in our syllabus we only have the discrete type stochastic process. So we are learning only discrete type stochastic processes, and here especially we will learn two types. One is called arrival type process, and Markov process. Okay, Markov process. You are not learning, so there is something called continuous Markov process also. So this is not in our syllabus. We are not going to learn this thing. We are going to learn the arrival type and the Markov process. Okay. Now what is an arrival type process? So I mean, what does mean by this kind of arrival type process? So arrival means what? Something is arriving or something is receiving by someone. So let me give you some. Um, oh my God. Okay, so let me give you some examples. So this arrival type process. Arrival type stochastic process. Okay, so maybe example. So I can give you say kind of uh, say quiz. Okay, so maybe quiz, yeah. So you know the quiz answer I am asking you. So maybe quiz reception at my laptop. Okay, these are all discrete storage process. So on some day I am receiving plenty, someday there are few, or someday there is nothing, right? No, so it's kind of, for example, today I'm going to ask you to submit uh, one tutorial. So today there will be no submission, probably tomorrow there will be few submission, and then if deadline is day after tomorrow, For example, deadline is 19, then 19 there will be lots of submission, and there will be some student who is going to submit even after 19, and then the submission will be this, and then there will be, so this is today 17, and then 18, then 19, and then 20, there will be something, and there will be some more student will submit on next day, like this. Okay, so these are arable type Stochastic process example. Then I am receiving this kind of thing, or maybe number of, maybe another example that you can say that uh, customers uh, comes to a shop, okay, or purchasing as a store, okay, or something, say completion of some job, you can say that completion of some job, completions of some job. These are all example of arable type Stochastic process. And then number 2, the markup process. So so the markup process. So one very important example is called simple random walk, that I will describe. Simple random walk. This I am going to describe later when I am going to study. We are going to study markup process. Okay, and there are many other examples. But simple number one, like you start with something, and then you go, and then come back, and then go, then go and come back, come back, come back. This is an example of simple random walk. Okay, this we are going to learn in future class. Okay, so now let us start with a specific type of arrival type or discrete type Stochastic process, and today, so let us start with this. This is called Bernoulli process. Okay, so what is a Bernoulli process? So let me write down definition, mathematical definition. So a Bernoulli process is a sequence of uh, independent Bernoulli random variables, say x1, x2, x3, with probability that xi is taking 1 means success or arrival, whatever you can see, probability of arrival or success. This is p, and xi equal to 0 is probability of not arrival or failure is 1 minus p. Okay, so this is a collection of such kind of collection of Bernoulli random variables, and you have For each case you have either probability either you have variables or success which is probability p, or you don't have a variable with probability 1 minus p, right? Now one can ask important question, what do you mean by independent Bernoulli random variables, where you have this is kind of a infinite sequence, right? Now you recall that we learn in the class independence of random variables for finitely many cases, right? If you have finitely many random variables, for example, if you have 2, 3, 4, then we learn it, right? Now the question is that what is the meaning of this independent uh, infinite sequence, independence of infinite sequence of random variables? So independentness. So just note that note. So the independent independent or independence of okay, independence of infinitely many, like when I say infinitely, I mean here countable infinite, okay? I mean here countably infinite, infinitely many random variables are, are random variables, okay? Say x size. So this is defined by the uh, fact that for any say natural number n, um, x1 x2 xn, or other in any set, I should say any set x t1 x t2 x tn. So this t1 t2 tn can be any natural number. So any set of these are is independent. Okay. So um, so whatever number of random you are choosing, if the number is finite, say you are choosing say x 100 position, x maybe x 51, x 100, x 1000, x 2005, whatever you choose, finitely many, and then you show that each of such finite collection is independent, okay? So this is the meaning of independentness of infinite collections, okay? Now for each of such Bernoulli process, so you can attach some random variable. So let me attach it. So you can say so random variable attached with or associated with a Bernoulli process. Okay. So number one, so you can ask so number of success. Maybe you can ask that. Okay, so let me write down. So you are doing say so you want to know the number of success number of success in and the fast in trials. Okay, and obviously you understand that is, so this is nothing but so number of success, maybe say you can write down some number here. So number is of success. So we can ask, you can say that this is having a probability mass function. If the number of success is k, then you choose how many out of n many k many success you can choose by n choose k many places, and then probability of success is k and 1 minus p to the power n minus k, right? This is probability of failure, and then your k can be either 0, 1 or n. You can have n success, like you'll have n places 1, 2, 3, 4, 5, 6, 7 in the n places, and you may have success, success, failure, success, failure, failure, success, something like that. Okay, so you are asking how many successes are there. Okay, so clearly this is nothing but a binomial random variable. Binomial. So binomial random variable is coming out of a Bernoulli process, and it is nothing but you are asking how many success one can get out of say in many trials. Okay, and you know that this kind of process has expectation of this number of successes in P if n is the number of trials and P is the probability of success, and the variance will be n into P into 1 minus P. This is already learned in the class. Okay, so this is one random variable. There is one another random variable. So now we can ask a different question. You can ask that how many trials you require for the first success. So you can ask how many number of trials required for the first success. Okay, so if the trial required is t, say t is the random variables, is counting the number for which you get the first success. Okay, then t has a PMF, t has a, obviously this is a discrete random variable. Okay, and what will be the PMF? So PMF will be, suppose PMF is at t means that before that t minus 1 many places you have a failure, each trial independent, so it is 1 minus p power t minus 1, and that tth one is success p, and t can be 1, 2, okay. So we can understand that this is nothing but a geometric random variable. Okay, and you obviously can know that the expected values of t is nothing but 1 by p, and the variance of t is nothing but 1 minus p by p square. Okay, so so this kind of a time you are checking before the first success. What is the time required? Time means it is first trials or second trials or third trials, like that. Okay, clear? So so you easily get two types of random variables. And now so here we are having some, okay, 1 minute. There is a black blank page. Yeah, so now I think it's fine. Yes. Now we will learn some of the properties of um, Bernoulli process. Okay, of Bernoulli process. Okay, so independentness is very important. So what does that mean? So uh, independent. So what does that mean? That means suppose you have so you remember that each of these so you have Bernoulli process x1 x2 and dot dot dot, and you can find out many random variable out of these. Suppose you have x1 x2 some x5, so this u1 will be a random variable. Similarly, you have another random variable, say u2, say x3 plus x6 into x2 x4 into x6. Okay, now can you say anything about u1 u2? So what can you say about what can you say about u1 u2? So the answer is u1 u2. So I mean one answer is u1 u2 are independent. Independent. What does that mean? That means, see here you see these xi's are independent, right? So and then this xi, x2, x3, x5 does not appear inside this. So these random variables are independent. So this is very important property. So if you generate many such things, random variables, so yeah, those are independent from the property of Bernoulli. And then you have another property, and there is one more important property, this memoryless property. So what does that mean? So memory lessness. So what does that mean? That means it does not remember say what is happening. For example, you are doing a Bernoulli trials, and you have first place, you have a success and a success, then failure, and you want to know what happened in the code trials, and it does not remember, it does not depend on whatever happened in before, right? So these future dependencies, you remember in my one of the question I said that we will try to ask this kind of question, the future dependencies. At fourth place, that so this is does not depend on the past. So in past what happened does not depend. Okay, so it can be either failure or success. Okay, it is itself is a um, itself is a random variable. Okay, clear. So this property is called memorylessness. So it does not remember the memory. Okay, and then one more important property you can ask. So this is depend on memoryless property itself. So you can also call it say fresh start property. So fresh start property. So this is depend on link with this memorylessness. So what does that mean? Suppose let me give an example. Suppose t is the time, so until the first success, until the first success. Okay, and that that there is no success in the first n trials. Okay. Now, can you say anything about? Uh, can you can you guess this unknown variables? So this n minus t many times. Okay. Can you guess what happened to this n minus t minus n many times? Okay. So this Frestas probability tells you that this t minus n. So if you want to find out what is probability, suppose t minus n equal to t. So and then given that t greater than n, then that means that the first success is not inside n many trials, and then you have only t many trials left, and to get a success out of the t many trials, one t minus 1 many trials will be failure and the rest will be t, right? So this probability will be this, and you can immediately understand that this is nothing but probability that t equal to t. Okay, so what does that mean? So that means um, so the probability that t equal to t and n minus t equal to t, they are same given that t greater than this. So this is, that means it is giving you a fresh start. So you have first in many places you have failure, failure, failure. If so this in many places, but when after in many places you start a new you kind of this in a new random variables with the same, I mean same random variables, but you can start with this is kind of again a geometric. So you remember this is a geometry distribution, the full thing. So you have a success here, all are failure. The whole thing is geometric, but if you remove this thing, again rest is also a geometric random variable, geometry random variable. Okay. So this is kind of your start, giving a new start after some time. Okay, clear? So this is one example, one problem property. So I can give you example also. So example to understand this problem. Okay, so so let me ask you properly. So let capital N uh, be the first time in which we have a success immediately after a success or following a success, immediately following a previous success. Okay, so what does that mean? That means both x n minus 1 and x n are success. Okay, so that means, so this means this n minus 1 and both are success. Okay, that is the meaning. Now question is that what is the probability, what is the probability that next to our immediately next to our failure. So I'm asking probability of x n plus 1 is the next of xn and x n plus 2, both are failure. Okay, this is I'm asking. So the question is clear. So suppose we know that in the place where you have first two success, okay, and you want to know the next two are also failures. Okay, what is the probability? Now you can either use this fresh start property and independent memoryless property of random variable Bernoulli process, or you can do classically. So let me tell you. So we using this. So the answer. So using this using the fresh start property. Um, so using this property, what you can say that whatever happened doesn't matter. It does not the next place probability of uh, x equal to n plus 1 equal to 0, it does not depend on whatever happened, and this is 1 minus p. Similarly, probability that x n plus 2 equal to 0 is also 1 minus p, and whatever we ask you, probability of x n plus 1 and x n plus 2 0, right? So what does that mean? That means it is the intersection of the probability, and these two, see, x plus 1 equal to 0 is one event, and then another event is x n plus 2 equal to 0, and because these events are independent, so we can write down this probability of x n plus 1 equal to 0 into probability of x n plus 2 equal to 0. Okay, and both having probability, so it is 1 minus p whole square. 1 minus p square is the answer. Okay, so this is, if you are using this property, you need to write down that uh, Bernoulli process IIT property, right? Or you can have a alternative solution. So second solution, classically. So what you can say, you can think that capital N itself is a random variable, right? So it's a random variable because it is the place where you are getting first time a success followed by a success, right? So so this is random variable. So you can using conditional probability formula. So now using uh, conditional probability, conditional probability. What you can say the probability that x n plus 1 equal to x n plus 2 both are failure, that depends on which position it is going to be having, right? So it depends on n. Suppose n is the place where you have first position, so you can write down this x n plus 1 equal to x n plus 2, both are failure, and given that capital N equal to small n into probability of capital N equal to small n, right? So this is the conditional probability formula, you remember that. Okay, now this formula tells you that this is nothing but right hand side you can write down as probability in n equal to n, running over n. So running over n means in from all over the distribution. Okay, so this means this is probability that x n plus 1 equal to x n. Okay, so I should say small n. Okay, so this is capital N and this is small n plus 1 n plus 2, both are 0. Okay, with n equal to small n. Okay, and probability of n equal to small n. Okay, so and now capital N and x's are independent, so this is nothing but this probability. So next page, so you can write down that this is nothing but sum over n probability of x n plus 1 x n plus 2 equal to 0, and then independent of capital N. So you can write down this conditional probability is the full probability into probability of n equal to n. Okay, and now we see that this first term is independent of capital N random variable, so you can come out, and this is nothing but 1 minus this product is already, you know that 1 minus b to the power this. Okay, and then you have this, right? Now capital N equal small n. This is what this is. This n is a discrete random variables, right? So this is the PMF of the discrete random variable n. And what does that mean? That means you are taking the sum of full random variables, and then this sum will be nothing but 1. So you are now ending up with 1 minus p whole square. Okay, which is, you recall that the value is same as value of whatever you got it previously. Okay, so either you can use the Freestyle property, other property, or you can also use the classical definitions. Okay, so maybe because this is a new idea you learn, so I will stop here, and maybe in the next lecture we will describe more properties and more problems on this Bernoulli process. Okay, so maybe I will stop here. Okay, so